Welcome to Glass Plate. We have done two examples of a presse-papier that was produced and had a temperature of 70 degrees and needed to be cooled down to an average temperature of 30 degrees. In the first example we did, we assumed that the air surrounding of 20 degrees surrounding the sphere had that temperature all the way up to the sphere, and we could use the graph. And we found that it took a little over an hour to cool this sphere to this 30 degrees. Then we realized in the second one that may not be the case that this temperature is all the way to the surface up to 20 degrees. So we introduced ad hoc a Nusselt number characterizing heat transfer on this side. And what we found that it took hours for the sphere to cool down. The second case is much more like practice, because there is always some resistance, and we learned that we need to get that resistance small. It was too big. In today's problem we're going to try and see how we get that resistance down. And the idea is that we blow cold air, 20 degrees air, around the sphere to cool it down. Basically what you do when you try to eat too hot food, you blow on it. And what we would like to know, what should the air velocity be if we will reach this temperature of 30 degrees within 2 hours. Again, we cannot use the graph because there will be resistance here. And we need to be able to model that. This is advanced, so I'll guide you through. I need something on the outside. The external Nusselt number should be connected to the flow. And there are relations for that. For instance, for flow around the sphere, we would have that the Nusselt number externally is 2, which basically comes from conduction, so no flow, plus a correction which is pretty big if the Reynolds number is high. The correction goes like this. Now, you may not know all these things, but it doesn't matter. I'll try and show you that this is not so difficult after all, once you know what this means. The Reynolds number, we've seen that is rho v d over viscosity. These properties are taken from air. Velocity of the air flowing around, d the diameter of the sphere. Prandtl is, let me take a peek that I write that down in the correct way. Mu Cp over lambda all of air. This I can look up. This contains the v that I know. Thus, Nusselt is a function of the velocity. I don't know this Nusselt, but I do see for a given velocity is the constant. So I can quickly use the result that we had in the previous example, where we said, okay, I need to solve a heat balance that is of this form. The rate of change of the energy, the thermal energy of the sphere, is equal to the outflow, a U times an area times the driving force. Everything is known here except for this U that is a constant. And I could solve this as we did, and we found that the temperature with respect to the environment temperature changes according to this rule. Minus 6U rho Cp d times T. These are taken from the sphere. D we know, U is unknown. Now we have T and required that T equals less than 2 hours, so we take 2 hours for it. That gives me a rule on U itself. I can compute U, and it must be 6.5 watt per meter squared Kelvin. if U has this value, then this relation tells you that after 2 hours, the mean temperature is 30 degrees. Okay, but I don't need to know U, I need to know the velocity, which is still embedded. So now I'm going to spell out that this U is connected to the resistances, an internal plus an external. The internal is written as Nusselt internal times the lambda over d internal from the material. And this Nusselt, we know, is 6.6, unsteady heat conduction inside a sphere. The external, H external, is Nusselt externals, lambda over the air, because it's outside the sphere, over d. I can compute from this rule, because I know the internal, I know the total U, what the external H is. And this must be, let me peek, 13 watt per meter square Kelvin. Oh, but then I can compute that that means that the external Nusselt number is 50. Aha. If I now know Prandtl, I look up what the properties of air are, then Prandtl is 0.77. I can back out what the Reynolds number is. So if I do that, I get out of this relation that Reynolds to the power 0.5 equals 79. Thus, Reynolds itself is the square of that, 6.3 10 to the third, and this equals rho air, V of the air, D of the sphere, mu of the air. I can look those up, and from this rule find that V is about a meter a second, which is reasonable. You can blow easily air with a meter a second around this ball. In summary, this is a more difficult problem, as the unknowns are hidden. But the bottom line is that we realize that the sphere is cooling down and that we can describe that via a heat balance where the change in energy is caused by outflow that we write in Newton's cooling law, where the heat transfer coefficient is made up of two parts. An internal one that we know, an external part where we have a Nusselt relation for. In that Nusselt relation is the unknown V, and I back that out to a meter a second. Try this one yourself. Just repeat what we discussed and see that after all, this is quite doable. If you don't follow it, don't get frustrated. This is the advanced level. This just shows you that you can design something like this, that you can back out with these type of calculations how hard you have to blow. Is that 10 meters a second, a meter a second, 10 centimeters a second? We know it's a meter a second. And you can do that and cool the system down within 2 hours rather than 21 hours.